the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on the videos.
Good day all, welcome to Smart View Guide tutorial. So we are going to solve this question on thermodynamics. You can see the question is very long and it asks us to make some calculations about an adiabatic system. So the adiabatic system is a cylinder that contains nitrogen gas N2 and a block of copper separated by adiabatic membrane. So whenever a system is adiabatic, we know that heat transfer is zero. Initially at stage 1, the pressure and temperature of the gas are 6 exponential pi Pascal and 270 Kelvin respectively. So let's have a depiction of the setup. So suppose this is our container. So this is our copper block. Here is our gas, nitrogen gas. So initially it is said that the pressure is 6 exponential pi Pascal while the temperature is 270 Kelvin. So the copper block temperature is 380 Kelvin and a heavy adiabatic frictionless piston M with a mass of 45 kg is pinned at a height of 20 cm above the surface of the copper. The copper block is 1 cm thick. So from this diagram, the thickness of our copper is 1 cm and it says a lid or a piston is placed 20 cm above the surface of the copper. So if this is the surface of the copper, it means 20 cm above. Let's say this, we define this height to be 20 cm. So here is a piston. Now the piston has a surface area of 50 cm squared and the density of copper is 8.96 gram per centimeter cube. The specific heat capacity of copper here is given and the gas constant also is given. So Cp of copper is 385 joule per kilogram Kelvin, and then the gas constant that is R is 297 joule per kilogram Kelvin, and the specific heat capacity at a constant volume that is Cv is also given to be 741 joule per kilogram Kelvin. Now assume ambient pressure is 0, absolute outside the cylinder. So we are asked to evaluate the mass of the contained nitrogen gas. Again, to find the mass of the copper, and then when the pin is removed and the piston settles to a new position, that is at state 2, we are asked to find the position of the piston in state 2 and the temperature and volume of the nitrogen gas in state 2. The first part of the question asks us to find the mass of the nitrogen gas. So we are going to use a relationship, that is a gas equation, P1V1 equals to mRT1. So M is going to be P1V1 over RT1. This is equals to divided by R, which is 297, multiplied by the temperature 270. So the obtained mass is 7.48 exponential minus 3 kilograms. Now the B part, we are asked to find the mass of the copper block. So now to find the mass of the copper block, the information given on copper, we are given thickness T to be 1 centimeter, which is equivalent to 0.01 meter. The surface area of the copper is equal to the area of the piston, which is 5 centimeter cubed, equivalent to 5 exponent minus 3 meter cubed. So this is a cross-sectional area of copper. So now we know volume is area times a length dimension such as thickness. So the volume of the copper block is going to be the cross-sectional area of the block multiplied by the thickness, which is 5 exponential minus 3 multiplied by 0.01, and this is 5 exponential minus 5 meter cubed. This is meter squared, this area. Now we know that density is mass over volume, so that makes mass to be equal to density multiplied by volume. So the density of our copper is 8.96 member in gram per centimeter cube. So we need to convert gram per centimeter cube to kilogram per meter cube. So we divide 8.96 by 1000 to make it in kilogram, and we multiply by 1 exponent minus 6 to convert centimeter cube to meter cubed. This is kilogram per meter cube. So this is going to give us 8960 kilogram per meter cubed. To be 8960 multiplied by this volume, which is 5 exponential minus 5. So here we are going to have 0.448 kilogram. That is the mass of the. Now for the C part, we are asked to evaluate the position of the piston at state 2. That is when the pin that is holding the piston is removed. So here is our piston. So something here is holding it in place. So when that thing is removed, definitely we know the piston is going to rise up. So we are asked to find the change in height. If this is, let's say, x equals to 0, that is when the piston at state 1. So at state 2, let's say it's state 1. So at state 2, we know that the piston is going to rise maybe to a new place like this. So this difference in height is what we are going to find. So for this, the pressure inside the cylinder will be equal to the pressure due to the height of the piston. And the pressure of the piston is equal to the weight of the piston all by the area of the piston. Since the pressure is force over area, this is mg over A. So the mass of the piston member is given as 45 kg multiplied by 9.81 all by the area of the piston, which is 5 exponential minus 3 meter cubed. This is going to give us 88254 Pascal or 88.254 kilopascal. So at state 2, we have P2 to be 88.254 kilopascal, but we don't have the volume of our balloon, and the gas constant doesn't change, is 297 joule per kilogram. Now the change in internal energy is given by Q minus W, but since Q is 0, remember it is an adiabatic system, it means the change in internal energy is going to be only work. This work is given by the formula mCv T1 minus T2, where Cv is the specific heat capacity of the gas at constant volume. So here you can see that we have T1, but we don't have T2. And since it is an adiabatic system, we are going to use this relation to find T2. That is T2 by T1 is equals to P2 by P1 to the power of lambda minus gamma minus 1 all over gamma. This gamma is a characteristic of its system, meaning each system has its own value. And the gamma is given by Cp by Cv, where Cp in this case is given by Cv plus R. This is 741 plus 297. This will give us 1038. That means gamma is 1038 whole by 741, which will roughly give us 1.4. So now you can say T2 will be equals to P2 over P1 raised to the power of lambda gamma minus 1 over gamma multiplied by T1. And this is my P2 is 88254 divided by P1 is 6 exponential 5 to the power of 1.4 minus 1 by 1.4 multiplied by T1, which is 270 Kelvin. And the final answer is 156.14 Kelvin. Now we can go back and evaluate the work done. So the work now is the mass of our gas, and we have obtained the mass of the gas in part A. And the mass is 7.4822 multiplied by 10 exponent minus 3 times Cv, which is 741, into the change in temperature, 740 minus 156.14. And the result is 631.24. Now, before finding the new height, we need to first find the volume at state 2. So we use the relation P1, P2 equals to V2 by V1 raised to the power of lambda. So that means V2 by V1 is P1 over P2 raised to the power of 1 over lambda. So that makes V2 to be equals to P1 P2 raised to the power of 1 over lambda having gamma multiplied by V1. So now V2 is 6 exponential 5 by 88254 to the power of 1 over 1.4 multiplied by V1, which is 1 exponential minus 3 meter cubed. So this is 3.93173 exponential minus 3 meter cubed. So as you can see, we have already solved the D part, while we are yet to solve C. We have found the temperature and volume of the nitrogen gas in state 2. Now to solve the C part, the volume is area multiplied by a length dimension. So in this case, the volume at state 2 is V2 multiplied by the area of the piston times the original height, which is h, plus the extension, which we have called x. So we have V2, we have the cross-sectional area, we have h, which was given as 20 centimeter from the question, and we are trying to find the value for x. So 3.93173 exponential minus 3 is equals to 5 exponent minus 3 into 0.2 plus x. I'll do a calculation and we'll find the value of x to be 0.5863 meter, equivalent to 58.63 centimeter. So you can see we don't need to do the D part because we have already obtained V2 to be 3.93 exponent minus 3 meter cubed. And, we have found T2 to be equals to 156.14 Kelvin. Remember, you can give your feedback in the comment section. Thank you for watching.